my name is Simone Matecna, and I did my project with Robi Rahman, and our project deals with regression through the lens of linear algebra and calculus. And we'll be taking you through our project and talking about the different things that we did to illustrate a simple linear model. So first we'll begin with the linear algebra perspective. And basically here, what we're always trying to do when we estimate a regression is we're trying to understand the relationship between points, and we're trying to fit that relationship as best as we can. So here we will define a simple linear model as the fraction of people in a tract or a county with a college degree, and the relationship between that and household income in that area. So this is how we've defined our model. And now we want to know the coefficients or the slope estimates between those two things. We want to know what is the relationship between those two things. And we can do that by representing this as a matrix. So we will define the matrix AX equals B. And what we're trying to solve for here is this vector of X, Y, and Z. But of course, we know that these values cannot be fitted perfectly. Otherwise, we could just solve for these values. So what we're trying to do is that we're trying to find a vector B, which lies in the column space of A, which basically means that we're trying to find a model that minimizes the error between the difference of these 2 points. So we're trying to minimize the error between the vector P and the observed vector B. And here, in order to do that, we need to choose a P that is perpendicular to the error vector, but that also points in the same direction as B. So we can invoke our linear algebra knowledge in remembering that in order for the error vector to be perpendicular to the column space of A, the dot product between them must be 0. And then solving for our x hat, which are our predicted values, or the slope estimates that we're trying to solve for, we see that we end up with this relationship. And in order to ensure that A transpose is always an invertible, that A is always an invertible matrix, we need to multiply both sides by A transpose, and then we are left with a symmetric square matrix that is always invertible, and we can solve for our x hat, which are our predicted values. And again, these predicted values is the estimated relationship that our studio or whatever programming software is doing under the hood to create this model between any number of variables. And this analysis was drawn from Dr. Chamberlain's lecture, and the source is cited there.
Another way to create linear models is by using methods of calculus for optimization. We can determine parameters for a linear relationship by finding the error between the data and our linear model as a function of the model's slope and intercept, and then differentiate there with respect to these variables. The optimal values for the parameters, which make the model most accurate and minimize the error, occur when these derivatives equal 0. Then taking these optimal values for slope and intercept gives us the line of best fit. These can be calculated analytically as through regressions using linear algebra or calculus, or graphically using contour plots, as we've also demonstrated below.
All right, so now that we have understood the mathematical motivation behind regression, we're going to demonstrate this understanding with an empirical exercise. So for our exercise, we used publicly available data from Opportunity Insights, which is a nonpartisan organization at Harvard that publishes data for other researchers, which is great. And the first data set that we use for this project is looking at characteristics at the county and tract level. And this data is taken from the 2000 and 2010 census tracts. So we present the data here. You can see that there are outcomes such as, the racial disposition of the county and the incomes of the county. We also have certain characteristics like the composition of the household. And if we wanted to estimate a simple univariate regression with this data, we can begin by plotting a regression, which is looking at the number of the share of members in a census tract with a college degree and the impact of that on mean household income in 2010. So we plotted this data using our regression, and you can see that the output for that regression is presented in the table here. And you can see that there is a very strong positive correlation between the household income and the share of people in that track with an advanced degree. So basically what this is saying is that if nobody in a certain county or track had an advanced degree, this would be the mean household income of that area. And if 100% of people had an advanced degree, this would be the mean household income that you could expect or that we would predict. So we plotted that using our ggplot, and you can see graphically that relationship. It's very obvious that there's a positive relationship. Our line of best fit is represented by this red line here. The gray shading that you see here, that would be the confidence interval, and you can see that that confidence interval is relatively small, which is good. It means that we're relatively certain of the relationship that we have fit. And you can see that that relationship, while it gets a bit fuzzier as you get a higher share with advanced degrees, it's fairly obvious that it's positive all the way through. And now we will move on to the second portion of our empirical exercise.
So to understand these relationships further, we've used another data set, also from Opportunity Insights, on some related metrics, reporting educational attainment versus parental income. So we've run another basic ordinary least squares regression, finding a similar positive relationship between parents' incomes and their children's high school completion rates. So this second data set reports, divides families up into 100 cohorts or percentiles by the average parental income, and then reports the children's high school completion rate for each of the 100 groups. So here are the results of the regression presented in this table, and then we have plotted them below on the next page. The black dots are a curve representing the data points, and the red line again is our line of best fit. So as the plot shows, as the previous plot showed, prevalence of advanced degrees in a tract was predictive of household incomes, but also from the second regression, high household incomes are in turn predictive of high children's future educational attainment. The line of best fit we get from this equation, or from this regression, is the equation high school completion rate of the cohort equals 0.00266 times family income percentile plus 0.7194. And as you can see, the correlation is very strong with R squared equals 0.96. So if we want to calculate the total error between the linear model and the observations, we can do so with this sum of squares formula right here. So S are sum of error as a function of M and B, where M is the slope in the linear model and B is the intercept, equals the y hat, which is the predicted educational attainment of a cohort, minus y, that cohort's actual observed educational attainment. Then we take the difference squared, and then we add up the sum over all 100 data points. And our prediction, since it's a linear model, is going to be the second equation there, y hat equals mx plus b, where x is the parent's income percentile, and then y hat is the predicted educational attainment for that cohort. So using a calculus method for this regression, we can differentiate S, the total error, with respect to these coefficients, M and B, and where the derivative is 0, the error will be minimized. You can do this analytically as computer programs do. We've also shown a graphical method below. So if you create a multivariate contour plot of the amount of error versus the variables M and B as we've done below on the next page, you will see that the yellow here is lower values of error, and red shading on the contour plot indicates high total error. So you can see that the error is low for values of m between -0.05 and 0.05, so the slope will be somewhere there. And then zooming in on the lightest yellow low error regions to the second plot, we see that the ideal values for the slope parameter will be somewhere between 0.002 and 0.003, and the ideal value for the intercept will be somewhere between 0.06 and 0.08. So if we go back up and look at the graph, we see that this is indeed correct. This visual model graphically confirms what we found analytically conducting a regression, where the equation is actually the line of best fit is predicted educational attainment equals 0.0266 times parents' income percentile plus the intercept 0.7194.
All right, and that concludes our project.